Alright, so let's continue. So multiplexers, demultiplexers, and so on. So basic 2-to-1 multiplexer. Two inputs, input 0 and input 1. One output and a select bit, and your select bit basically chooses which of these inputs goes to your output. So if select is 0, I0 goes to out. If select is 1, I1 goes to out. So it's a steering circuit, right? It has all these pipes coming in, and it says which pipe should I connect to the output. And from 2-to-1s you can build a 4-to-1, from 4-to-1s you can build 16-to-1s, and so on and so forth. And one of the things we did with MUX is, if we have a 4-to-1, any function of two variables we can implement with this just by tying your inputs to whatever value you want. So if we wanted to make an exclusive OR gate, which looked like that, all we got to do is feed those values into these inputs. And now if your input is 1, 0, that's going to select input 2, that's going to send a 1 to your output, there's your 1. If your input is 1, 1, that's going to choose input 3, which sends a 0, there's your 0. And if you put in 0, 0, that's going to choose input 0, which we set to a 0, there's your 0 on the output. So we can implement any truth table that we want using multiplexers. And this is what FPGAs do internally. They have multiplexers and they set up the inputs according to whatever you configured the device to do, and it acts like a truth table basically. So these are called LUTs, sometimes lookup tables. And it'll say how many LUTs you have in your device and so on. Those are basically your random logic elements. So multiplexers work like that. Demultiplexers go the other direction. So a demultiplexer might have one input and 4 outputs. And a select, and you can choose which of these outputs should be driven from your input. And so you can put a MUX on one end, a demux on the other end, and you can use a single line to send multiple pieces of information from one side to the other, as long as you synchronize your select lines. 7447, that's the decoder for the 7-segment display. You don't need to know details of that, but it's an example of a decoder, which in this case takes in 4 values and gives you 7 outputs. And those outputs are the ones that you set up to the segments of that 7-segment display to display a digit based on the 4-bit value you're sending in. So that's a decoding process. Priority encoder I'm not going to ask you about, but priority encoder was this thing that tells you the priority level of the highest priority input that's active. So if your first input is the highest priority and that's got a 1 on it, your output would be a 0, to say input 0. If the first input that's active is input 5, then your output would be a 5. Right, so we'll touch on those in 270 also. Programmable logic. So PALs, PLAs, and PROMs, and fuse maps. So somewhere. Alright, so there's a typical fuse map. Bunch of wires. But these all kind of work the same way. You have inputs that we could usually have going in from the left, but we farm those off. So this input here actually runs vertically along this line. This third input comes across here and runs vertically on this line. Right, so we have these long vertical lines that carry our inputs, or the inverse of our inputs. So here's an inverse of that second input, and it runs on this vertical line. And then we have horizontal lines crossing those that feed into a gate. So these are all AND gates. And you just make connections between vertical and horizontal. So if I make a connection between this vertical line and this horizontal line, then it means this input here is being fed into the input of an AND gate. And we can have multiple inputs driving inputs of that AND gate. And so we can generate product terms along here. And those product terms in this particular device, they all get ORed together. So there's an OR gate, OR gate. And then the output in a pure PLA or PAL or PROM would just go into an output port. On these devices, they actually go into flip-flops, and they have some feedback, so we can build sequential elements. But the fuse maps that you've seen on homeworks or on the midterm, that's as complex as we need to go. So mostly it's just inputs with inverters and so on, AND gates, and then OR gates. And when you want to show a connection, we typically just draw an X.
Here, as well, gates could you possibly use like active gates or like.
Say again?
Somewhere in the fit now, is there an extra extension you can put in to include a target? Or
I don't think I've seen programmable devices with XOR gates built in, but usually you can do an XOR with just a sum of two products, and so it's pretty easy to, right? And we don't usually make these maps by hand. These are usually done by software. So your software will certainly have a way to specify an XOR, and then the compiler would just turn that into, you know, A and B bar or A bar and B. XORs are really useful sometimes, right? They're good for parity generation, we saw that, and other things, but they're not universal the way that NANDs and NORs are, and the way that a sum of products is. So I don't think I've seen those in devices like this before. All right, half adder, full adder. How much do you remember about those? Hopefully everything. So you know how to add numbers on paper, right? And the whole deal with a full adder, it takes in two bits A and B, and it takes in a carry in, and generates a sum and a carry out. And a half adder is full adder, where we just assume the carry in is 0, so it's slightly simpler. And if we're laying these out side by side, we can make an n-bit adder by having n full adders, and the carry out from here feeds the carry in of the next stage. And if we're doing that, there's no carry in that comes in on the rightmost bit, so we can assume this is a 0. But rather than taking a full adder and tying that to 0, we just make a half adder, which is a slightly simpler circuit. And you've done homework questions on this. You had a few different versions of lab experiments related to this. So just make sure you're comfortable with the truth table, how you would implement that. I'm doing invisible things. There you go, full adder. So carry in, carry out, lay them out side by side, carry out from here feeds the carry in on the next one, and so on.
What's the output on the bottom?
That's just a sum.
Oh, okay.
You can make a 32-bit adder with 32 full adders laid out side by side, and you make a 32-bit multiplier with a 32 by 32 collection of full adders, right? That's a lot of full adders. It's 1024. But you can do that, and it's not ideal, but it works. All right, so sequential versus combinational circuits. So combinational circuits, you can define the behavior by looking at the truth table. The combination of inputs specifies the outputs. Sequential circuits also depend on the history of things, okay, the sequence in which the outputs have changed in the past. And that was the whole latter part of the course. So we started talking about propagation delays, and basically just be aware that if you have any kind of physical gate, when one of these inputs changes, the output doesn't change right away. It actually takes a little bit of time. So if this is A and B and C, and A is high, and B starts off low and then it goes high, C is not going to go high right here. It's actually going to take a little while. So this difference in time, that's the propagation delay. And we usually use tau for time, and so tau sub t might be propagation time. And so that introduces the possibility of glitches, and we've looked at some circuits that have glitches based on this behavior. So the one we actually did in Verilog was something like this. Right, and the output should always be 1, because if x is 1, we've got 1 going into an OR gate. If x is 0, that gets inverted to a 1, we've still got 1 going into an OR gate. So in either case, we expect the output to be a 1. If you actually make the timing diagrams, there's a glitch where the output goes low. Right, it happens when x changes from 1 to a 0.
I have a question on half adders and full adders.
Yeah.
Do we need to know the circuitry to build it?
You should be able to, you can either put that on your notes or memorize it, but you should be able to produce it.
Okay.
Right? You definitely want to be able to produce the truth table. And there's a nice little trick here. If I write my outputs in the order carry out and sum, this is just the 2-bit sum of the 3 input bits. Right? So this is a 0, this is a 1, this is a 2, this is a 1, this is a 2, this is a 2, and this is a 3. And then you can write equations from that. And they're pretty simple equations. The sum is just an XOR, which you kind of have to recognize. And the carry out is just those. But it's not bad to put on your note sheet. All right, we talked about latches, and then we never did anything with them after that. But latches were the building block for what we did use, which was flip-flops. So a basic latch is typically a pair of inverting logic gates. And I always have to try it in my head to figure out which one would be set and which would be reset. But you just run through it and figure it out. If this is Q and this is Q bar, to make this a 1, we need zeros going in here. Well, we need zeros going in there. We need a 0 there. So if we want a 0 coming out, we need to have an R. So this has got to be, I don't know. Need zeros. If we want Q to be a 0, then we need a 0 coming out here. We've got to have a 1 going in. So that's our reset. That's our set. So 1 here will force the OR to be 1, force the NOR to be 0. And that'll put a 1 out on the top. But like I say, we didn't use these. We used this to build a D latch. Right, so have a D input and a load line that drives either the set or the reset line. but then we turn those into flip-flops. And flip-flops, the big deal with flip-flops is they're edge-triggered devices, right? This latch acts based on the value of S and R, right? Anytime S changes, something happens to the outputs. A flip-flop changes only when the clock ticks. It's on that edge, either the rising edge or the falling edge. And we like flip-flops because they help us avoid glitches. Right? The inputs can change a million times, but until the clock ticks, they have no effect on the flip-flop state. So let's just use a clock to synchronize everything. So that's why we have edge-triggered devices. And the classic example to motivate that was a shift register. And you've done shift registers in your lab, and we've done them in class, but you did them in a few labs. Right, if these are D flip-flops, and your clocks are all tied together, then when the clock ticks, everything moves down one spot. Right, if these were level triggered devices, as soon as I raise this, everything races through all the way. Right, so that was that I equals I plus 1 that just kept counting in the beginning of talking about sequential elements. So flip-flops, D, JK, and T, right? D output just matches the input. JK we just did on the state machine example, and it's just got that peculiar but very useful third state where both inputs are 1 and the output toggles. And T flip-flops are kind of a subset of that. If T is 0, it's stable. If T is 1, clock ticks, the output toggles. So flip-flops have, in addition to propagation delays, they have setup and hold times. Setup is how long the input needs to be stable before the clock ticks. And hold time is how long it has to be stable after the clock ticks. So you're setting it up in preparation of the clock, and then you're holding it after the clock. And you can't change it like as soon as the clock ticks. You gotta wait a little bit of time. Flip-flops also come with presets and clear inputs sometimes. So a preset input says set the output to 1, regardless of J and K or T or whatever the other inputs are. Clear input says set the output to 0, regardless of the other inputs. And sometimes those are synchronous, which means they only take effect when the clock ticks. Sometimes they're asynchronous, which says I don't care what the clock is, I don't care what the J and K inputs are. If I raise this line, set the flip-flop to a 1. Right, so that would be an asynchronous preset. And those are useful when you build state machines because you can make a reset button that puts you in some initial state. If you want to start in state 0, you tie all your reset lines to the big red button and you label it reset. As soon as you push that button, all the flip-flops output is 0, now you're in state 0. So it lets you initialize your circuitry. And everything we've talked about is synchronous logic, so we've always had a clock in our system. We can do asynchronous design. It was popular in the 80s, it got popular in the 2000s, it keeps coming back. Because the clock really kind of slows us down. It says we can only do things, 3 billion times a second, if it's a 3 gigahertz clock. You can do asynchronous, but then you've got all the problem with glitches and timing issues that we've been trying to avoid by having a clock. But if you can take an async course sometime, go for it if you like this stuff, because it's cool. And then finite state machines, so FSMs, these get a gazillion problems on homework, which was an awesome job, by the way. Basic setup, memory, combinational logic, and feedback, and some set of outputs, and some set of inputs. That's every state machine. So flip-flops, their outputs drive combinational logic, possibly in conjunction with inputs, and that generates the inputs of the flip-flops, which will determine the next state when you have your clock tick, so there's always a clock. Okay, there's every state machine. And when you're working with these, you want to know if the outputs depend only on the state or if they also depend on the inputs. Okay, and that's our two sort of classes of machines. So mealy out is a function of state and the inputs. A Moore machine, your output is a function just of the state. So if you have a Moore output, you can put that in the circle that lists the state. You can just put a line, put the value of the output underneath, because it only depends on the state. If you have a mealy output, which also depends on the inputs, then you have your state, but you have an arrow saying if the input is such and such, we're going to take this transition, so you can list your output on that arrow. So input outputs, Mealy-Moore machines, how to show outputs. Maximum clock frequency, I don't ask you to calculate that, but you should know it anyway, right? Maximum clock frequency is how long it takes all your logic to basically go through this loop. So it's the propagation delay in the combinational logic, which means find your longest path from input to output and add up all the propagation delays. That's a hard thing to do. And then you also have to wait whatever the setup time is for these flip-flops, right? Because once the outputs are finally correct here, you can't tick the clock right away. You still have to wait for that setup time to pass. And then you can clock the tick, and if the hold time was long enough that the outputs might change again, you need to take the hold time into account. But usually we can ignore the hold time, because once the outputs change, it's going to take a while before those changes trickle through, and we change the inputs. That's usually longer than the hold time. So it's really the setup time plus the propagation delay. That's how much time you need between ticks. So that's your minimum period. Reciprocal is your maximum frequency. All right, and we talked about how to do synthesis, and analysis is just the other direction, the easier direction actually, right? If you start with a state machine, you write equations for the inputs to the flip-flops, you take your states and, where's my sample state machine? There's our sample state machine. So you start with this, you can write equations, right? And from that you can know what flip-flops do, and so if J1 and K1 are such and such values, you can figure out what the next values of the state are. And from that you can fill out your state transition table and then draw your diagram from that. So that's the analysis direction. The synthesis direction we did, which was take your diagram, state assignments, turn it into a transition table, and then draw your circuit. And that leaves us with nothing but Verilog, which we've been doing for a few weeks. So Verilog, I'm not going to grill you on syntax, okay? I would never even pretend to suggest that I know Verilog syntax by heart. Right? I don't. I find code that I've written and I just modify it. So should I have a semicolon here? Do I have to say begin, end? Not worried about those things, okay? So high-level versions of Verilog. Wires and registers, okay? Wires for something that we're going to use an assign statement for, probably. Registers for something that needs to remember a value, which usually means it's something that's inside an always block. Because always blocks, we don't say assign, we say this thing, arrow that thing. And it says at this clock edge, we want to copy this into this other thing. If you copy into a register, it'll remember it, right? So usually those left-hand sides in always blocks are registers.
What did you say wire was used for again?
Wire is mostly for assign statements, right? And for assign statements, get friendly with the ternary operator because it's really useful. So 2 to 1 mux. So we want to build that circuit. If select is 0, output is I0, otherwise output is I1. We can do that with one assign statement. Assign out equals, and then we use this ternary operator, select equals 0, question mark, I0 colon I1. So if select is 0, this says assign out equals I0. If select is not 0, this says assign out equals I1. This works in C, this works in Java, this works in other languages, but also works in Verilog. And it's a nice compact way of writing an if statement. And so out could be a wire here, because we're actually saying connect it to this expression. And this actually gets synthesized as a multiplexer. Test benches, I'm not going to ask you to write a test bench because those are a pain also, but basically a test bench is just something that we use to set input values on a circuit we want to test, and then typically we monitor the output values somehow, either with a display statement or we use something like GTK wave or some other way to look at the outputs, and then we can change the test bench and, you know, interrogate the circuit in different ways. Definitely know the always statement, and the main way that we've used always is either always at positive edge or always at negative edge. And this is whatever your clock is, typically it's clock, but that's just a name. And so there is a begin, I remember that, and an end. And so everything in here happens when that signal goes in that direction, either rises or falls. And when we're inside here, we don't want to say assign. We want to use this arrow. All right, so. And basic if then else. If condition, do this, otherwise do that. I think that's our whole course. So you could have just come today and you could have skipped the other 10 weeks. So there's a lot of stuff in 250, right? I mean we really cover a lot of different topics. And if you're computer science, right, this stuff will help with computer science. All the Boolean algebra and such comes up in programming. State machines come up in programming a lot, actually. Because when we write code, sometimes, you know, you want to read some numbers from the user and then do something. But more often than not, we want to read some numbers from somewhere, but we want to do something based on what we saw in the past, right? So when I move my mouse, my cursor moves around the screen, right? And when I click my mouse, you know, it generates some kind of event and some code happens. Well, the code that runs when I click my mouse varies wildly depending on where my mouse is pointing, right? So you can't just write code that says you click the mouse, let's go ahead and show the person what the weather is, right? Because if I'm over here and I click my mouse, I want to show my Wi-Fi status. If I'm over here and I click my mouse, I want to see the weather. So you need to know what's happened in the past in order to know how to respond to something that's happening now. That's a state machine setup, right? And that happens in code all the time. So you'll see these concepts in other forms. If you're computer science, CSE 215, discrete structures, we do a lot with Boolean algebra. We come back to De Morgan's theorem a few different ways, and you know, it's just one of these things that kind of permeates everything. De Morgan's theorem applies to set theory. It applies to abstract algebra. It comes up in all kinds of different forms. So even if you never touch digital logic again, right, the concepts in here pop up in a lot of different areas. So it's useful the more you see them and the more different contexts you see them in. And if you're electrical engineering, right, you're going to do more of this stuff, obviously. So any other questions or comments? Thoughts, concerns? So you got 9 questions on the final.
How many are they worth?
I think they're mostly 10 or 15. So however that worked out to be 100. It's probably a unique solution. Well, we got 20 minutes. I can let you go 20 minutes early if you want. Or we can talk about 270. You want to call it quits 20 minutes early? Let's go for that. It's hot.